today. And today's presentation, we are going to talk about stepwise analysis, step-by-step analysis that you will find in the options if you go to a regression or an ANOVA. The way we're going to deal with that today is regression. So the example I have here on the screen is a regression example that we use during our trainings. And what we are going to do in this example is we are having a look at a manufacturing plant, and we're going to try to explain and be able to predict the energy consumption, how much energy, how much electricity the plant uses when it functions. And we have two types of factors. We have environmental factors that are column 1 to column 5. So just the month, the mean, minimum, and maximum temperature. You can see that we're using American units. The percentage of sun that hits the plant. And then we go on to factors that are more internal. So we have the number of unit produced, the total equipment runtime, the employee hours, so how many hours do we work, and the average equipment age, how old are the machines that we are using. So first, I want to start doing this analysis manually, just to remind everyone how we normally do that manually, what are the big principles we have to respect. And from there, we're going to move to how can we automatize this and have some kinds of help in Minitab. So just as I said, the goal here is to build a model that we can use to predict the energy consumption of our plant. We would normally go to Stat, Regression, Regression, and choose Fit Regression Model. Here we have to enter the responses, or response. In our case, we just have one, which is the energy consumption, and the predictors that we want to use for our analysis. I want to use all of them. We normally start with all the predictors we have registered, and we'll see why in a second. Click on OK. And what Minitab does is something most of you or all of you already know, is an ANOVA table, analysis of variance, to tell us if each factor is significant or is not significant, and if I should actually keep these factors in our model. The way we do that is that we have a look at the p-values that are given by Minitab, and the normal reference is to use a p-value of 5%, so 0.05, to decide if a factor is significant or not. If the p-value is under 5%, it is significant and we keep it. If it's above 5%, it's not significant and we don't keep it. So in our case, what we would do is have a look at all the factors, all the p-values, select the highest one, the month, and get rid of that factor. Redo the analysis and do this type of procedure several times until we get only factors that are significant. We're going to do that in a second. Just before doing that, I'd like to remind you how the p-value is determined. P-value is a very practical tool for us because it gives us a fixed reference. We work with 5%, and that's above or under 5%. This is the international reference, and that's it. In some cases, you can work with a different reference, maybe 10%, maybe less, but you have a fixed reference. And what Minitab does is it determines the p-value from the f value. The f value is the result of a calculation. It's the raw result that we are not able to analyze unless we have the corresponding tables. So means have a look at the tables and translate that into a p-value. The way the f-value is determined is it's a ratio between the variation introduced by each factor. So we have here the adjusted mean square, so the variation introduced by each factor, and we compare that to the variation introduced by the error. The error being everything that is not considered by our model. So I've got variation introduced by the month, the temperature, the sun, everything in my model, plus something that is not accounted for in my model, and that's the error. Okay, so what we do here is we take every factor and divide the variation introduced by each factor by the variation of the error. So here we have something that is close to 50%, and you can see that the number here, so it's 37230, is roughly half of the variation here in the error, which is close to 80,000. So that's where the f values come from. So in that case, the bigger the f value, the more important the variation introduced. The more important the variation introduced, the lower the p-value, because the more significant is going to be our factor. Because of that, because we calculate that in that way, when I'm going to remove the month, which is the first we're going to remove, this 2017 won't be accounted for in my model. Because it's not accounted for in my model, it will translate, it will transfer to the error. So when I remove a term, all the p-values and the f-values can change in the next model. So this is why we don't get rid of 3 or 4 factors at the same time, but just one by one, because the p-values are going to evolve. I cannot just start this and say, okay, the only valid factor here is the total equipment runtime, so I'll just keep that and get rid of all the rest. We'll see that it's not the way it works. So let's proceed with the manual analysis. So here I have the month, it's the less significant. I'll go back to my dialog and get rid of the month. Click on OK. And here you can see that I've got a new analysis without the month. And if I have a look at the p-values, the mean temperature is 0.618. And if we have a look at the previous analysis we did, the mean temperature had 0.648. So we can see that this has changed a little bit. We're not going to go through every single factor, but it's just to illustrate that the p-value is changing little by little. So the next step is to have a look at the second less significant factor here, which would be the employee hours. So I'll go back to my dialog and get rid of the employee hours. Click on OK. I'll keep doing that until I get only factors that are significant. So the next one, I'll just do that quickly. Next one is the mean temperature. So we'll take the mean temperature out. Click on OK. Now we need to get rid of the minimum temperature. Okay. Now you see that the maximum temperature went from not significant, here maximum temperature 0.19, to significance. So you can see here that the way I build my model when I remove some factors can have a real influence and make a factor significant or non-significant. Then I've got the percentage of sun time. So I'll get rid of that. Okay, and we'll just finish off by getting rid of the unit produced. So units produced, necessary to really understand what we're doing. And here we get to a model with three factors. We have the max temperature, the total equipment runtime, and the average equipment age, which is still not significant, 0.8, so 8%. If I'm working with 5%, I need to get rid of it. If I'm working with, let's say, 10%, I could argue that, then I would keep it. In our case, we're just going to use 5%, so I would take that one out. And here I get to my final model, in my case, which doing by hand would get to be max temperature and total equipment runtime. The difficulty with that is it's very manual. It can be a lot of work if we have even more factors, more data, the interactions, the second degree, third degree orders, etc., etc. So if you have many, many factors, it can be a bit long and quite a lot of work. So in Minitab, you have ways to make that more automatic. We're going to see a few today. So if I go to Stat, Regression, and Fit Regression Model, I'll just get back to using all the factors, so the initial situation that we had just a few minutes ago. I'll go to Stepwise that you have here. And here you see that I've selected none, which is doing the analysis manually as we just did. And if I click on the list, I have three choices. I'll go from bottom to top. Backwards elimination is just what we have done manually. So we start with all the factors, we take the less significant, we get rid of it. Second step, second less significant, etc., until we only have significant factors. Forward selection is the exact opposite. So I'll start with one factor, selecting the most significant of each factor taken separately. And then I'll add a second factor, a third factor, etc., until I'm not able to get a factor in because none of the remaining factors are significant. And then you have the stepwise, which is a combination of the other two. So you can put things in, but if something becomes non-significant, you can then take it out. So it's a bit of a mix of both. What we're going to do today is have a look at the forward selection, have a look at the backward elimination, which we did manually, and then we'll have a look at a third method, but stepwise being a combination of the two, we'll skip it for today. So I'll start with forward selection, so starting with one factor and then progressing to more factors. You can see that if I choose in the list of potential terms, I can force a factor that I want for some reason to appear in every single model I'm going to do. So I could do that. We're not going to force a factor. And here you see that I have an alpha level to enter. And I've said before that when we do things manually, we use an alpha level of 5%. In forward selection, we use an alpha level of 25, stepwise 15 and 15 to enter and remove, and backwards elimination 10%. These all have been determined to be safe. What we want to do, because we're making things more automatic, we don't want Minitab to just get rid of many factors and then realize that, well, really we would have been interested in considering these factors. So we buy ourselves more margin to be able to finalize the model manually if needed. So here we have this alpha. It's predetermined by Minitab, but if you need to change it for some reason, you can. And here at the bottom, you can have options to select a table for the model selection detail, either just the method or in each step that we're going to take. So I'll check each step so that we have more information and we're able to have a deeper look into that. Click on OK, and we get to this result. So you see we have step 1, step 2, step 3. Here we have our factors, and you can see that the first model is the constant plus a first factor. So the first factor we have is the total equipment runtime, which is very significant, and we just start with that factor, which is the most significant we have. Then we have a look at the other factors and see if we can add another factor, and we add the maximum temperature. And the third step, because we have that margin, Minitab adds the average equipment age. So here we arrive at a model that was our step here, the one before last, with 3 factors. Okay, and we could either manually go to the last step that we've done before, or argue that we want to keep that factor for some reason. Just as an example, a good reason in that case to keep the factor is when we consider a factor, we always consider the cost of controlling that factor, because if it's very expensive to control, maybe it's not worth it because we don't gain a lot of precision. So here the factor is the average equipment age, which is something that really costs us nothing to control. Okay, it's the age of the machines that we use. We know when we've bought these, so we know the age of the equipment. We could argue that because it doesn't cost us anything, I want to keep it in the model. That's entirely up to you. Another thing that's going to be interesting here is that we see the evolution of the R squared and the R squared, the predictive R squared, if you want to predict things. So you can see the evolution of your model. And here at the bottom, you're going to have all the information about the final model. So here we have 3 steps, and we get to where we were manually, or almost. If I want to do the opposite, I'll go to Start, Regression, and now in Stepwise, instead of choosing forward selection, I'm going to choose backwards elimination. So the exact opposite, which is what we've done before. So here you can see that the level of alpha is different. I've got 10%, and I'm still going to include the details of each step. Click on OK. And here I have, of course, more steps because I'm going down to 3 factors again, but I start with all of my factors, so my 9 factors I think we have here. So first step is where we started manually, and the less significant factor is the month. You can see that in the second step we've gotten rid of this factor. We take the second less significant, which is going to be employee hours, and do a third step without that one. And you can see in every step we have an evolution of the p-values, and we have an evolution of the R squares, the malloc and the S, the variation. So we can really understand what's happening during our analysis. Step 3, we get rid of the mean temperature that has disappeared here in step 4. Then we have the minimum temperature and so on. So the next one is the employee hours, the next one is the percentage of sun, and the last one is the unit produced. That gets us to a model, again, with 3 factors: maximum temperature, total equipment runtime, and the average equipment age. In our case, in this example, we get to exactly the same model. It is possible that in some cases you would get results that are not exactly the same, but they're going to be comparable. Because this is all automatized, what I would recommend if you have the time, and this takes a lot less time than doing it manually, is to maybe try out the three methods, the stepwise, forwards selection and backwards elimination, and see if you get the same results or not, see what models gets you what you want or what you need, because between one model and the other, maybe on a practical level, that's going to mean something for you, and one model is going to be easier than the other to use. To give a further step, we've seen the step-by-step analysis. Today, I'd like to have a quick word about, in regression, again, the best subset. So it's yet another tool to make things a bit more easy. So best subsets is going to give us the best factors that we can use to build models of with a certain number of factors. So let's say here I have 9 models, 9 factors, and I want to consider models with 1, 2, 3, 4, 5, up to 9 factors, which would be the best models at each level. So here I enter in response energy, predictors, all the others as we had before. Go to options, and here I can choose the number of models of each size that I want. So number of models with 1 factor, number of models with 2, with 3, etc. We're going to start with 1, and then I'll illustrate with 2. Click on OK twice, and I get this table as a result. So here you have the number of variables from 1 to 9, which are my factors. And here above the x's, you have the factors. So you can see written month, mid temperature, minimum temperature, max temperature, etc. So the first line is, if I have to use only one factor, and that's what I want, which ones should I choose? And the answer is the total equipment runtime. That gets me the best model I can get with only one. So it is the best subset of factors to have a model with one. I've got the R squared, malocp, and the S that will also allow me to see the evolution of the precision of my model and its relevancy, and then I'll be able to do some arbitrage between two different levels depending on what I want to do. If I want to choose the best model with only 2 of these factors, then I can add the maximum temperature, and here we get again to the model that we had built before. So we end up with the same result in that case, giving us the total equipment runtime and the maximum temperature. If I go for 3, again, I have the average equipment age, which is something that doesn't cost me anything to control. So again, I could discuss the relevancy of one versus the other, and the decision is entirely up to me. And then we go on with 4, 5, 6, 7, 8, and 9, so including everything. And we're going to be able to choose with the reference, with the indication of the R squared adjusted, predicted, malocp, and MDS. So I've told you that I was going to have a look at what happens if I go to 2, OK, and OK. So with 2, I get a table that's going to grow bigger. And you see that I've got 2 models with 1, 2 models with 2, 2 models with 3, etc. Of course, 1 model with 9 because that includes everything. So 2 models with 1, it tells me, well, the best one you can use is total equipment runtime. If for some reason you cannot use that, then the next best would be to use maximum temperature alone, knowing that there is a huge difference in the R squared. But on a practical level, it can be that I cannot control and use a certain factor. So this would be the use of that. With this, I'm reaching the end of the presentation. We've seen the automatized analysis and the best subset today, and we can have a few minutes for any questions that you might have. Please don't hesitate to go ahead with